So in one of the last videos I talked about functions, and I'm still using purple apparently, but function representations. So function representations, you have several different things that get utilized across math. You have the basic table of values. And basically the table of values represents some x and y pairing, and let's say negative infinity, dot, 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 dot. Let's do negative 3, 3, negative 2, 4, negative 1, 5, 0, 6, 1, 7, dot, 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 infinity, infinity. Now basically that's a table of values, okay? So that's one way in which we can represent a function, okay? Now another way we use functions are graphs, okay? So a graph, and normally what I have students do is I have them draw a graph of the table of values, okay? And so basically, if you draw a graph, you know, hey, at 0, and we'll do x and we'll do y. Okay, so at 0, I'm up at 6 along the y. So 1, 2, 3, 4, 5, 6. And basically, this is the point right here. That point right there is 0, comma 6. Blue represents y, red represents x. At negative 1, I'm at 5. Okay, so at negative 1, I'm at 5. Okay, so right there. At negative 2 along the x, so this is negative infinity, infinity along the x, and then this is infinity of the y, and this is negative infinity. And basically the whole reason why we have infinity set at these points is because as you think about functions, we tend to think about them as either increasing or decreasing. So we basically kind of want to look at what happens to these sets of values right here as I look at the interval or length along the domain, and basically what happens in my output. Am I increasing as I go to positive infinity? So as I go to positive infinity, I'm also going towards positive infinity, so it's increasing. So you can keep drawing the points if you want. At negative 3, so right here this value is at negative 3, negative 2, and negative 1. Basically, and at 1. At negative 3, I say I have 3. Okay, so negative 3, I'm at 3. Well, basically what happens is you get this function that just keeps going through all these points. Okay, and you get an increasing value. So as x goes to in positive infinity, so too does my output, which is basically what I can see right here. So this is a graph. So this is the second representation. Okay. A third representation that is commonly used in high school math is a mapping diagrams. Okay, you've got a list of x and you've got a list of y. Okay, and basically what they do is they just plug in random values. Let's say negative 3 and negative 2, 0, and 1. Well, over here, and we're going to use red for x, and basically we use the y, the blue for y. So at negative 3, we had 3, 4, and 0 was 6, right? And 1 was 7, right? And so basically what happened is x got mapped onto 3, negative 2 got mapped to 4, 0 got mapped to 6, and 1 got mapped to 7. Okay, so this is basically, we've got the table of values, the graph. This is a mapping diagram. Another way and term use of vocabulary is that it's also called a function map. And that's the correct term that's commonly used throughout math. Basically, we can also tell whether or not things are functions if we look at the mapping. If -3 had gone to both 3 and 4, that would be a contradiction because 3 cannot equal 4. So therefore, it's, it's not a function. Okay, so therefore, the function of x does not exist. Okay, so it cannot equal a function of x. Or in essence, y does not equal y. Okay, and basically what happens is the output's not the same if I plug in the same behavior, because ideally, if you plug in one number, you should get the same output no matter what for it to be a function. Okay, and that brings up another topic I'll discuss later on. But that's function mapping. Another thing is we like to use a list of values. Okay, so we use a list of values, a list of points. Okay, so I'll use the same points. So I've got -3, 3, -2, 4, and then 0, 6, and then I've got 1 and 7. Now basically you can deconstruct this in another set and basically say, hey, x is this, y is that, and if your x values ever repeat, then it's not a function. So -3, -2, 0, and 1. Basically I pulled out the first pairing in each coordinate point. Okay, and then we get some y value, right? So the y values. So when x is -3, y equals 3. When x is -2, y equals 4. When x equals 0, y is going to equal 6. When x is 1, y equals 7. So basically, I can determine whether or not the list of values is a function or a relationship by looking at these values right here. If any of these values repeat in the list of numbers, then it's not going to be a function. Okay, so these are some basic ways in which we represent functions. We've got the table of values, we've got the graph, we've got the mapping diagrams or function maps, is what mathematicians call them, and we got a list of points. There are other values like set builder notation and stuff like that, but those are or conformal mapping. A conformal mapping uses a lot of function maps and a lot of lists and a lot of set builder notation, but we're not going to talk about that in this video. You'll learn about that in a different video. So I hope this helps with understanding function representations and understanding what a function is. Next video I'll talk about domain and range, and then we'll get on to the topic of linear functions and the basic things that you need to know in statistics to understand the difference between continuous functions, discrete functions, and probability and cumulative distribution functions.